Hi everyone, this is Rohan, and in this video I am going to explain the analysis of three hinged arches subjected to uniformly distributed load throughout its span. Come, let's learn. Now, usually this analysis is asked in the exam in the form of a proof, and the question goes something like this. For a symmetrical three-hinged parabolic arch subjected to uniformly distributed load throughout its span, prove that the bending moment and radial shear force at any section is zero. So what we have to prove is that the BM and RSF at any section is zero if in a three-hinged parabolic arch, which is symmetric in nature, is subjected to a UDL throughout its span. So to begin with, let us consider a three-hinged parabolic arch ACB, which has a span of length L and a central rise H. Now let us consider a UDL of W kilonewton per meter acting throughout the span, and as soon as the UDL is applied, the support reactions are going to come into play, which are vertical at A, horizontal at A, vertical at B, and horizontal at B. So our first task is to find out the support reactions, and for that we are going to start by using the equations of equilibrium. So the first equation of equilibrium that I am going to use is summation of f of x is equals to 0, and I will consider the forces towards the right side as positive. There are two forces towards the there are two horizontal forces here. One is HA, which is towards the right, and one is HB, which is towards the left. So according to this equation, it will be HA minus HB is equals to 0. Now I can simply write that as HA is equals to HB equals HA equals to HB, and let us call that as equation A. Now the second equation of equilibrium that I'm going to use is summation of f of y is equals to 0, and I'm going to consider the forces in the upwards direction as positive. The forces in the vertical directions are VA in the upward direction, this entire W into L, that means this entire UDL in the downward direction, and VB again in the upward direction. So this equation becomes positive VA minus W into L plus VB is equals to 0, and simply I can write this as VA plus VB is equals to WL. Let that be my equation B. Now I am going to use the third equation of equilibrium, that is summation of moments about A is equals to 0 clockwise positive. I would just like to mention here that I could have also taken summation of moment about B is equals to 0. It would have given me the similar results only. Okay, summation of moment about A is equals to 0, and clockwise moments I am considering as positive. So you see, first of all, HA and VA will not have any moments at A because it is passing through A. Moreover, HB will also not have any moment about A because the line of action of HB is also passing through A. So the two forces only that we need to consider is firstly this UDL, okay, and secondly this VB. So let's see how I'm considering this. Right, so this UDL is going to have a moment about A in the clockwise direction, therefore it is positive. Again, moment is equals to force multiplied by the perpendicular distance from its CG, right? So the entire load is W into L, but the CG of this UDL will act at mid-span. So therefore, I am multiplying it by L by 2. Next, consider this VB load. This VB load will have a anti-clockwise moment about A, hence it is minus, and the perpendicular distance between VB and A is L. So therefore VB into L is equals to 0, and if you solve this, you will directly get that VB is equals to WL by 2. Now if you put the value of VB equals to WL by 2 in equation B, you will get that VA is also is equals to WL by 2. Now if you see, we are yet to find out the value of HA and HB. Now for that, I'll be considering the fact that this C is an internal hinge, and therefore bending moment about C is equal to 0. Now what is bending moment? Bending moment is the the bending moment at any section is the algebraic sum of the moments of all the forces either to the left or to the right of the section considered. So here in this case, I am going to consider the section towards the left of C, and the sign convention for that is sagging moment is positive and hogging moment is negative. To simplify it, in the left of section I will have clockwise moments as positive and anti-clockwise moments as negative. So keeping that in mind, let's see about C. We will have to consider three forces. One is this VA, one is HA, and one is just this part of W, right? This half span here of W, because we are considering to the left of C. No need to consider anything towards the right. So let's see it one by one. So first, considering VA, so VA is going to have a clockwise moment about C, so it will be VA multiplied by L by 2. Distance between C and A is L by 2. So VA into L by 2 minus because HA is going to have a hogging moment, or should I say anti-clockwise moment about C. So therefore, it will be HA multiplied by the perpendicular distance between HA and C, that is H. And lastly, you see, this W is also going to have a anti-clockwise moment about C. So therefore, it is going to be a little cautious here. Just see, the load is W into L by 2, because the span here is only L by 2, and the distance of this small part about C will be half of L by 2, that is L by 4. So therefore it is multiplied by L by 4. You already now know the value of VA, so put the value of VA here, simplify this term as WL square by 8. So therefore you will get that the value of HA is equals to WL square by 8H. Please understand that this is very important for you, and this itself sometimes comes in your exam as a prove that in case of a symmetric three-hinged parabolic arch, if there is a UDL acting throughout the span, prove that the horizontal reaction is equal to WL square by 8H. Now, if I put this equation E back in equation number A, putting E in equation A, I will get that HA is equals to HB. So therefore HB will also be equals to WL square by 8H. So you see here, we have found out the value of VA, VB, HA and HB. So our first step, that is finding out the support reactions, is done. Now let's move to our second step, that is finding out the bending moment. In order to do that, I will consider a section x dash at a distance x from A. If you can see here at the figure, I have taken a random section x dash, and it is at a distance small x from A. The reason why I want to do that is because if I am able to prove that at this section the bending moment is 0, then since it is a random section, it will also prove that at any section it is equal to 0. So now, if this distance is x, right, the corresponding distance here will be equal to y. Now what is this y? Just see that since ACB is a symmetric parabola, therefore this is y is nothing but the equation of the parabola, that is y is equals to 4hx L minus x divided by L square, where h is the central rise and L is the span. Okay, and I can simply write this as, I just simplified this term, so it becomes 4hx divided by L minus 4hx square by L square, right? Just normal simplification. So now let us find out the bending moment at x. So at this point I am finding out the bending moment. Okay, reminder, what is bending moment? Bending moment is the algebraic sum of all the moments either to the left or to the right of the section. I'm just going to take the left because it is much more easier that way here. And if I consider that towards the left, so what is the sign convention? Clockwise is positive, clockwise moments are positive, anti-clockwise moments are negative. Let's start. So here I will have the first load as WL by 2. WL by 2 here multiplied by X, and this is causing a clockwise movement. So therefore it is taken as positive. WL by 2 multiplied by X. Next, here this WL square by 8H, this is going to have an anti-clockwise moment, right? It is going to have an anti-clockwise moment. So WL square by 8H multiplied by the perpendicular distance between this load and C is, sorry, this load and X is Y. So WL square by 8H into Y. Then thirdly, if you notice this W, it is only acting for a span of X. It is only acting for a span of X, and also it is making an anti-clockwise moment about this point X. So what we get here is W into X is the load, and then again furthermore multiplied by X by 2, because if X is the total distance, then CG will lie at X by 2. So this is the equation that I am working with. In this equation, let me just simply put the value of Y is equals to 4hx by L minus 4hx square by L square. I got that value from here. Okay, I got that value from here. Now if I just simplify each and every term here, just open the brackets of everything, you will get WLX by 2 minus WLX by 2 plus wx square by 2 minus wx square by 2. So you see the first and the second term is getting cancelled, the third and the fourth term are getting cancelled. So ultimately I can write here that the bending moment at x is equals to 0, and since x is a random section taken, so therefore we can conclude that the bending moment at any section is equals to 0. So that ends our step 2. Let's quickly move towards step 3, which is the determination of radial shear force. Radial shear force. Now in order to find out radial shear force, you should draw the free body diagram of the left side of section XX, right? I would ask you here to please redraw the diagram. So you can draw only left part of the section of XX. So what you are actually doing here is you are cutting off this part. You are cutting off this part. Now once you have cut off this part, what happens, since this is a rigid structure, what will happen is you are going to release a horizontal reaction and a vertical reaction here, right? So the horizontal reaction at X, let it be called HX. Now this HX is nothing but the axial force at that point. And if you notice, there are no horizontal loads here except for WL square by H. So by default, HX becomes equal to WL square by 8H. And as I told you, a vertical reaction will also come here. Let us call that as Vx, right? And here you see Vx is nothing but the shear force at the X. Here shear force, if I want to find out at Vx, first of all, what is shear force? Shear force at any section is the algebraic sum of all the vertical forces either to the left or to the right of the section. Okay, so here we have two vertical forces. One is WL by 2, right, and the other one is W kilonewton per meter, which is acting for a span of X. So W into X. WL by 2 is in the upward direction and WX is in the downward direction. And the sign convention for shear force is that left of the section upward forces are taken as positive and downward forces are taken as negative. So with that, Vx becomes WL by 2, right, since it is in the upward direction, minus Wx, which is in the downward direction. Now just see that at this point, let me draw the tangent. Now I am drawing the tangent, and let this angle be theta. Let this angle be theta with the horizontal. So radial shear force is going to be perpendicular to this tangent. Radial shear force will be perpendicular to this tangent. Okay, now in order to find out the radial shear force, I need to resolve Hx and Vx in the direction of radial shear force. So let's quickly do that. Hx, if I resolve in this direction, it will come out to be Hx sine theta, and it will be in this radial direction only. And if I resolve Vx in this radial direction, it will be Vx cos theta, but in the outward radial direction, right? inward and outward. So here, if I want to write the equation of RSF, if I take this inward direction as positive, then RSF will be equals to hx sine theta minus vx cos theta. Now you see here, the value of hx and vx are available with us, but sine theta and cos theta, we need to find that. So in order to find that, we will have to go back to the equation of parabola, right? Equation of parabola. And we will have to derivate the equation of parabola. Let's do this a little slowly. You see, in this first term, since we are doing dy by dx, 4h by L is constant and dx of dx is equals to 1. So the first term becomes 4h by L minus, keep it as it is. Again in the second term, you see 4h by L square is constant. So 4h by L square is as it is, and d by dx of x square is equals to 2x. So this is multiplied by 2x. So let me, okay, multiplied by 2x. So now again we know dy by dx is nothing but the slope, that is tan theta. And just by simplifying this, I get 4h by L minus 8h by L square, right? And again we know tan theta is equals to sine theta by cos theta, right? And here what I want to do is I want to keep the denominator same, so I am keeping it as L square. So 4h get multiplied by another L, and minus 8hx is as it is. So can I say that the numerator and the numerator are the same and the denominator and denominator are the same? Yes, I can do that. So therefore sine theta will be equals to 4hl minus 8x and cos theta will be equals to L square. Okay, so now if you see the previous slide, we know the value of hx, we know the value of vx, we know the value of sine theta, we know the value of cos theta. In order to find out RHX, simply I will put these four values, right? And I will open all the brackets. If I just open all the brackets, I find that it is WL cube by 2 minus WL cube by 2. And then I have minus WXL square by 2 plus WXL square by 2. So here the first and the third term gets cancelled and the second and the fourth term gets cancelled. So radial shear force also is equal to 0. Again, since X was a random section, it is okay for us to say that radial shear force at any section also is equal to 0. So that brings us to the end of the proof that was asked, that is usually asked in your exam, that in symmetrical three-hinged parabolic arch acted upon by a UDL throughout its span, prove that the bending moment and radial shear force at any section equals to 0. But as far as the analysis is concerned, you must be knowing that there is one more thing that is called as the normal thrust, and this can also be asked in the question that can you prove that in this case normal thrust at any section will not be equal to 0. So if you have understood this, you can pause this video for a while here and you can try to solve this and come back, and then we will discuss about how actually to go about to solve this. Please take your time. All right, welcome back. Now if you have unpaused the video, uh, let us see slowly that whether you have followed the correct approach or not. So in finding out normal thrust also, we are going to follow the same kind of steps that we followed for radial shear force. That is, we need to draw the FBD, that is the free body diagram of left side of XX dash. So let us draw that. We already know this. Then we already know that HX is going to be WL square by 8H. VX is going to be WL by 2 minus WX. I am not going to explain this in detail because this is already explained. Then we draw the theta, and then here comes the new thing. Normal thrust is in the direction of the tangent itself. Normal thrust is in the direction of the tangent itself. So now we need to resolve hx and vx in the direction of normal thrust. So what do we have here? We have here hx cos theta, right? And here we have vx sine theta, both towards nt only. So therefore, if I have to write down the equation of nt, we have hx cos theta plus Vx sine theta. Now again, sine theta and cos theta, the values are known to you. Since the angle is the same, the values will also be the same. So simply I will put this four values, okay, and then I will open the brackets, and then maybe I will simplify it a little further. But even while simplifying it, how much ever you may simplify, right, you will never get 0. I will tell you why. Even if x is equals to 0, even if x is equals to 0, then these last two terms will become 0. But W will never be equal to 0, H will never be equal to 0, and L will never be equal to 0. So these two terms will always remain. So I can tell here conclusively that normal thrust in this case will never be equal to 0. Such a strange case, isn't it? In a case where shear force, normal radial shear force is 0, bending moment is 0, but normal thrust will never be equal to 0. So let us summarize this very quickly here, that for a symmetrical three-hinged parabolic arch subjected to UDL throughout its span, the vertical reactions at support is WL by 2 and WL by 2. The horizontal reactions at support is WL square by 8H. The bending moment at any section is equals to 0. The radial shear force at any section is equals to 0. But the normal thrust at any section is not equals to 0. So that brings us to the end of our analysis of symmetrical three-hinged parabolic arch subjected to UDL throughout its span. I hope that was useful for you. If you have any doubts, you can write in the comments below. Thank you for your time.